Okay, it's my pleasure to introduce Gail Grancharoff from Florida International University, who will speak to us today about non-Kähler manifolds via mapping tori. So thanks.
And this talk, which is, I should say, immediately joined with Anna Fino and most of the results with Beatrice, Brianza also. In fact, most of the work on it was done by them, so I'm more like observing collaborator in the case. And clearly, most of the slides are prepared by them, but if there are any mistakes, it's because I try to make changes. So, do you hear me?
Yeah,
Okay.
yeah, we hear you.
Let me know from time to time if there is a trouble.
No, it's
Yeah,
fine.
because
Now we hear you.
Yeah,
it's
it's been okay. Yeah.
Okay. So, this is one of the relatively recent constructions in terms of Kähler manifolds complex, and it's based on this so-called mapping torus. It's too slow. Yes. And the construction is topological, relatively simple. This is a quotient of the interval times a manifold by this type of identification, where the endpoints of the interval are identified, but the points of the manifold are slightly shifted. And this actually induces projection onto the one-dimensional circle with the standard fiber M. Now, this is a smooth fiber bundle, meaning all fibers are diffeomorphic, but it's not principal. And the structure group is the cyclic group, finite or infinite, determined by this diffeomorphism F. Now, yes, given space and a diffeomorphism, another way to represent this quotient is, in fact, to consider the product M with R and a quotient by the group Z. Now, one can easily see that the pullback of the one form, the generating one form on S1 is also closed one form on the suspension and nowhere vanishing. And there is this kind of reverse statement that a compact manifold is a mapping torus, if and only if it admits this kind of non-closed, non-vanishing, but closed one form. And I will mention that some of the basic working examples of solved manifolds and new manifolds in at least non-Kähler complex geometry are examples of this type of construction. And for that, what we started a few years ago with Anna Fino and Misha Verbitsky first, and then involving Beatrice, is to understand a little bit what kind of metrics or what kind of geometry will appear. Now I'm reminding here the Kähler condition, which is, well, probably everybody knows, so I shouldn't pay much attention. And then what are the corresponding generalizations I'll consider? The first order conditions, replacing the Kähler, wait a second, maybe I should do something different. I hope you still hear me.
Yeah, we can hear you.
Yeah, good.
Okay. Now, because the connection is really shaky. And now, the first was called balanced, and the other was called SKT, which is standardly called pluriclosed already. We used SKT as short abbreviation from Stone-Keller with torsions, which physicists use. And the first result known is if we have one metric which is both balanced and SKT, then it's necessary Keller. Now, there is a conjecture that if we have one balanced and another SKT, the manifold still admits a third possible metric, which is Keller. And this, well, let's say in the non-compact case, this is not true, meaning there are examples which admit one balanced, another SKT, but do not have Keller because of the subspaces. And the definition of the balanced will appear in a second, is given by Michelson, although this is equivalent to what before that Alfred Gray called, I think, semi-Keller. And this condition appears in some kind of natural decomposition of the tensors, which have symmetries of the covariant derivative of the complex structure under the unitary group. One of the components is precisely the component satisfying this condition. Now, the balance has this nice property that a metric is balanced permission if and only if we have this nice Keller identity for the Laplacians of the del bar and d operators, but only on functions. And the other, which actually we have used several times, is the so-called dual condition in terms of the positive currents of b degree 1, 1. And this is what actually Michelson used to show that some spaces do not admit balance metrics already. And the basic example, of course, is this Calabi-Ekman, that it doesn't admit balance. On the other side, the spaces which do admit are a lot more. I guess I should start with the Twistor space of four-dimensional self-dual Riemannian manifold, which is known from before. And the most interesting property here is that this is a condition preserved by bimeromorphic transformations of, in general, in particular, bimeromorphic space to a compact Keller manifold is always balanced. Another basic examples are these compact quotients of unimodular complex Lie groups are always balanced. There are these conifold transitions of the labial threefolds, meaning smoothing of a singular Calabi-Yau threefold. which is obtained by shrinking some special curves of normal bundle O minus 1 plus O minus 1, something important in physics. And again, for non-compact simple Lie groups of inner type with invariant complex structure, they actually do admit balance metrics, which, well, is in a sense opposite of what the compact ones do. The next examples I'll go over relatively fast. I hope you'll see it in the screen in that a solved manifold is balanced if and only if the Lie algebra has balance, meaning it will have necessary invariant balance metric in a sense. And the classifications of this type of compact quotients of Lie groups, some classifications are given here. You can see the list of various properties. This almost abelian means still solved manifold, which is two-step and has abelian ideal of codimension 1. Then the construction I'll look today is precisely coming from this suspension, but I'll need a little more information about it because this is the interesting thing is that this suspension construction eventually provides both balanced and purely closed metrics, and they depend significantly on the properties of this diffeomorphism. Now, I'll start with this motivating example, which was basically construction of these guys Qin and Wang. I'm talking about Botong, Wang, and Li Qin. This six-dimensional, real six-dimensional non-Keller who are diffeomorphic to complex Calabi-Yau non-Keller and symplectic Calabi-Yau, meaning symplectic with vanishing first-chain class. And I should mention that this is actually similar to previous construction by Magnusson, which actually the guys used. And the question, what kind of metrics do they admit, is what started basically the project and its follow-up. And in order to answer, I'll recall briefly this construction. I mean, it's not hard, but it does produce some kind of specific type of example, which I don't know from other way to exist. And one starts with this so-called Kummer surface. A Kummer surface, this is a K3 type surface, which is obtained by, well, taking a four-dimensional torus, but with a complex structure. That's why here notation is T2. So C2 factored by a lattice. And the lattice, well, one can take the lattice to be the standard one using the basic vectors. And then one can factor the torus by this involution of the group Z2, which is 1 and this involution sigma. And the result is the quotient is not smooth because it has 16 double points, I mean 16 orbifold points. And after one resolves the 16 points, which means blowing them up, one obtains 16 embedded curves, which are actually CP1s, the rational curves, of self-intersection -2. And suppose that we consider the set, which is the union of these curves, This is the so-called exceptional divisor, and of P. And one can see that the holomorphic two-form dz1-dz2 induces first nowhere vanishing two-form on the tori, and then its pullback on X induces holomorphic 2-0 form on the Kummer surface, which actually never vanishes. Now, what we want from here is, this is a classic construction, but we want this diffeomorphism, and one of the main advantages of this construction by Qin and Wang is that this diffeomorphism is almost explicit. In particular, if we take any matrix with, let's say, Gaussian integers as entries, meaning complex numbers with integer, real, and imaginary parts, and such that the determinant is 1, but the trace is greater than 2. Now, it's suppose that it's diagonalizable. Then, of course, the eigenvalues are the one eigenvalue and its reciprocal. And the absolute value of at least one of them greater than 1. Because obviously, otherwise the sum cannot be greater than 2. And one can take the, let's say, denoted by dv1 and dv2 the vectors for corresponding eigenvalues. Then what happens is that this A, okay, wait, okay, so what happens is that this A, the matrix, preserves this form, which is again 2-0, and also preserves the exceptional divisor D. In particular, it defines holomorphic transformation on the Kummer surface. And the holomorphic transformation preserves the holomorphic 2-0 form. Now, the interesting point is that because the eigenvalue, at least one of them, is strictly greater than 1, it appears that such map or such holomorphic transformation cannot preserve any Keller metric. So it's not isometric for anything. And well, it's kind of reasonably and pretty obvious. Then from this, we want to construct not just the suspension, but in fact, a complex manifold. And the complex manifold comes from the suspension pretty much times S1, times this S1 here. And if one considers this tori times the real line times S1, this is the corresponding action of the generator of the Z action. And the quotient, let's say we denote it by A of Kummer, has, first of all, trivial canonical bundle. And here trivial means holomorphically trivial. So this is Calabi-Yau type space. But it has two important properties. First is that it is formal in the sense of Sullivan, meaning the minimal model of the de Rham algebra is formal. And this actually follows from direct calculation. This is true, more general, not just for Kummer surface, but for any Keller, because the suspension from a Keller space is necessarily Keller. This was a theorem by Tischler. Is formal, I mean, and this is a direct calculation. But there is a statement which is that this space is actually not only non-Keller. It is not homotopy equivalent to Keller. Even more is true. Any direct product of this space with Keller space, again, is not homotopy equivalent to Keller. Now, this is one of the essential parts of this paper by Pin and Wang, the proof of this fact. And it uses relatively delicate theory, well, not really complicated, but delicate, which is developed by the second author there, bottom Wang, the so-called cohomology jump loci. And one uses just if one needs only the fact that it is not Keller, not in terms of homotopy only already, one can use Magnusson's proof, where it uses the fact that A cannot fix any Keller class, not just Keller metric. It cannot fix any Keller class in the Kummer surface, which is relatively easy to check at the end. Now, the next is the next point is this construction. When we started looking at it, is relatively straightforward to extend to any hyperkeller space instead of just Kummer surface. It's not going to be that explicit, but the properties which are important, which we want to be preserved, actually depend on the choice exactly of this homomorphic automorphism, which automorphism means complex automorphism, not not isometry here. Now, this is called hyperbolic if the action has a unique eigenvector with eigenvalue greater than 1. Now, using this kind of hyperbolic automorphism, and this could be for any Keller manifold and a lattice in C generated by two elements, one can use, well, we call it hyperbolic toric suspension, which is associated with this pair of maps in the product M times C, and the corresponding quotient by Z2 is generated by these two maps, given psi1 and psi2. In particular, again, one can see that the hyperbolic toric suspension is actually diffeomorphic to the product of the toric suspension and S1. Now, for hyperkeller manifold, the reason one can that hyperkeller spaces are interesting is that they actually admit such hyperbolic automorphisms. And in fact, they admit hyperbolic automorphisms which preserve the homomorphic symplectic form. Again, no Keller class, no Keller metric is preserved, but the homomorphic symplectic form is. And one thing we noticed after some work is this fact with Anna and Misha, that this type of hyperbolic homomorphically symplectic suspension admits a balanced metric. Now, this balanced metric cannot come from nice metric on the Kummer surfaces, for example, and something from the tori, because this automorphism F does not preserve a metric. And in these terms, the way to do it is actually implicit. The proof is using exactly Michelson's characterization of balanced metrics, and more precisely the second part of her paper, where we use this projection. The projection, of course, of a suspension is S1, and this homomorphic suspension is over the tori, which is S1 cross S1. And then what one can do is to use a theorem from Michelson, which says that this kind of map surjective onto a complex curve produces a balance if it is once it is vibration, produces a balance metric if it is proper in curve terms, which means that one can extend the cohomology classes of a fiber globally in a certain way. I mean, one has to see the paper by Michelson for more precise formulation. Again, we don't need the Kummer surface or hyperkähler. We can use the tori. And the first thing one can notice is if instead of the Kummer surface we have a tori, real four-dimensional tori or complex two-dimensional tori, this suspension, again, does admit a balance metric, it's known, but in fact it is almost a billion solved manifold. And for A, the metric actually can be found explicitly as invariant metric. But nevertheless, this we see still as a problem. Can we find explicit balance metric on this Kummer suspension, homomorphic suspension? And here I should mention that the words explicit are up to some metric on the Kummer surface, even not necessarily explicit, but some nice Kähler metric on the Kummer surface to be used because, well, we know that Calabi-Yau metric and Ricci flat metric on the Kummer surfaces really explicitly are not known. Just if necessary to use it, one needs to know a little more. Now, the next result is that once we know that there is a balance metric, the next is to check what happens with the pluriclosed. And the things to notice is that this suspension for hyperkähler space admits hyperbolic one, DDC exact and strongly positive PP current for any value of P greater than 1. For P equals 1 means it would not admit balance, but actually it does. But for any P greater than 1, one can construct this type of current. And this is the dual characterization of this fact that S does not admit any metric, which is P pluriclosed for any P at least 2. Now, actually, n minus 1 is the dimension of n. So the suspension is one more dimension. It's not, one should not be mistaken here. Now, the proof is actually one which Misha Verbitsky found initially. We need to rework a little bit, but the idea stems from the fact that for a hyperbolic suspension, which actually exists for most of these known hyperkähler examples, like Hilbert schemes of points of K3 and so on, F has unique eigenvalue lambda greater than 1, such that the action of F star on H2P has lambda P as the maximum eigenvalue. And then the set of positive PP currents, if they have bounded mass, which we actually want, is in fact a compact set. So in particular, we can construct a positive PP current with this property, where this is actually eigen current of the induced transformation F. And this is again as a limit of a system. Then one can look at formally the space of the PP currents, not positive, just PP. And fiber-wise, this looks like infinite dimensional. Okay. Let me see. Yes. Infinite dimensional local system, meaning locally flat or flat bundle. And the real line bundle is a sub bundle there, which is preserved by the flat connection, right? Because the monodromy map preserves is pretty much multiplication by lambda. So the line bundle is preserved, not necessarily the current itself. And then one can consider this type of form, lambda, or actually current, on m times r, which is well defined. Lambda power negative t is smooth. So smooth function times the current is still well-defined current. And then the corresponding positive PP current is given by this here identity, which looks like almost explicit, but it still uses some implicit limit sequence. So it's not necessarily that implicit. And now we go to the corresponding SKT condition. Now, again, this is a definition which you know very well, pretty much everybody from the people I know in the meeting. And we use the terminology SKT, but it's known as pluriclosed or one pluriclosed for a metric which has scalar form DDC closed. Here, this is the imaginary part of the del bar, or del operator, actually. And this is actually one of the weakenings of the Keller condition, which is in fact linear from the fundamental form, but still linear, but still it involves a second order derivative, so it is definitely more complicated. It's related with the fact that if one needs P pluriclosed, then for P equals to n minus 1, one can always find this well-known Gaussian result that after conformal change, one can get this DDC closed n minus first power of the corresponding metric. Now, in particular, when this number n is 1, this means every complex surface admits to the reclosed metric. Now, what kind of structures one gets out of Hermitian? What kind of metric connections one gets out of Hermitian structure are the ones which are determined by a torsion. Here, T is pretty much a parameter, and I don't give here the definition, but okay, I see that the connection is slow. Why? Okay, the connection should be okay now. Now, in this family of connections, which Gaussian defined, there is one which corresponds to -1 value of T, for which the torsion is actually totally skew symmetric. And for the value T equals 1, the corresponding connection is the so-called Chern connection. It has trivial 1-1 component, the torsion. And for the value 1, when one has skew symmetric torsion, the connection is called Bismuth or Strominger. In a certain way, Strominger is the first one who noticed the existence and in certain way uniqueness because the torsion was fixed of this connection. But Bismuth is the person, the guy in math who actually used in non-trivial way this connection for a proof of something which is called local Riemann-Roch theorem, meaning method of proof of the Riemann-Roch theorem. One can find explicit representatives for the curvature terms when this connection is used. Now, these are the standard formulas, and we call that the metric is SKT if and only if the torsion is closed. This, of course, is because the torsion itself is dc of the Keller form omega. Now, the basic example for such spaces still is the so-called Samuelson spaces, which are the, well, formally compact semi-simple Lie groups times a real space r power k, so that this is even dimensional. And this manifold admits nice invariant complex structure. The corresponding torsion is closed, and also the parallel. On top of it, the connection is flat. And there is this result from 2020 that up to a finite cover, the local sun and soul spaces, which are given by this already factor, are the only compact bismuth flat Hermitian manifolds. Now, another examples of these spaces, which one should know, is nil manifolds and solved manifolds. And here there is quite a few. There are quite a few papers. If one wants to look at other non-flat examples, which are only SKT and are still simply connected, there is this construction for principal toric bundles, which we had with Kuhn and my brother, which eventually leads for every positive K, this type of spaces admit this structure. I mean, for K greater than 1, this structure is not flat. The corresponding bismuth connection is not flat. Now, it's in a sense natural and partly straightforward to extend this construction from principal toric bundles to any principal bundles for which the structure group is even dimensional unitary, special orthogonal or compact symplectic, because they also admit nice flat and SKT matrix. I mean, the fibers in that construction. Now, the last type of condition I'll consider, which is the point of the talk. Now, one is the CYT. CYT, again, this is physics notation, coming from Calabi-Yau with torsion. And, well, to have 3-letter abbreviations is good. I mean, I think we should start looking at structures called FBI or CIA at some point. But so far, CYT is like the closest. And we use that definition for the bismuth as the trace. Here, of course, here the is implicitly understood. Okay, I guess the connection. So here is implicitly understood that there is summation over I. Now, again, the form here represents the first chain class. In particular, the first chain class vanishes if we have such metric, but it doesn't mean that the canonical bundle is trivial in holomorphic terms. It does mean that the holonomy of the bismuth connection is necessary, the restricted one is necessary in SU. Now, the interest over this matrix appeared from this paper, by Jeff and Gankian, considering the geometric so-called generalized Ricci flow. And again, it's clear in this case that if one has this form proportional to the metric with the constant equal to 0, then this is also reasonably called bismuth Hermitian Einstein. I don't know, maybe some people will argue should be bismuth Schrödinger Hermitian Einstein, but then we are going away from the 3-letter abbreviation. It's probably not a good idea. So up to now, the only known examples are in a sense kind of trivial. Well, trivial means Keller-Ricci flat are trivial. Then we have bismuth flat spaces, which necessarily are CYT. And of course, the product, because the products are. Now, the examples which are only CYT without being SKT exist again a lot. A moment. Have to wait a little bit until we turn this to the next page. Yes, and the easiest are any compact complex homogeneous space with vanishing Furchin class, which admits also the so-called invariant volume form, also has that CYT metric. Here, the appropriate deformation means deformation to another invariant complex structure, which actually on the so-called semi-simple part is compatible with the bi-invariant metric. Otherwise, it's not does not admit CYT necessarily. And here, of course, the way to show this is, in fact, to use some kind of a structure theorem type of homogeneous spaces, which admit invariant volume form. And for them, there is something which is called, again, Tits fibration, which is still principal torus fibration. But the base is not just Keller homogeneous space compact, but Keller homogeneous direct product with solved manifold, complex solved manifold, which is parallelizable, complex parallelizable, so it becomes something clear how to do. I would mention before I go further that it seems that invariant volume form, when you have vanishing Furchin class, should be a consequence, but I personally couldn't prove it first. And second, if one doesn't have invariant volume forms, there is a sequence of examples many years ago, maybe 30 or more, which actually show that the automorphisms groups, the biholomorphism groups of complex manifolds, which are non-Keller, actually may increase exponentially with the dimension, which, as you know, as long as you have metric, it's actually quadratic in dimension at most, the growth. So this type of examples and their geometries, the geometry of these examples are still quite mysterious to me at the moment. Now, going back to SKT and CYT, the standard problem now open is to find metrics which are both SKT and CYT, but not necessarily bismuth flat. And in fact, not just not bismuth flat, but not necessarily a product of this bismuth flat. And okay, so I'm back, I hope. So they are not a product of bismuth flat and Keller-Ricci flat spaces. Okay, and there are non-homogeneous examples, which in fact, even in dimension 6 complex spaces, which admit one SKT and another CYT. But to admit both is not clear. In a sense, it's up to some choices, which at least it's not obvious that one can solve together. Okay, I guess you don't hear me still.
No, it's okay.
I'm
We're
sorry,
hearing you, I think.
but
Okay.
yeah. Yeah, you hear already. Now I'm waiting for the slide to change. And I'll start with this non-Keller C space definition. which is essential ingredient of that compact complex homogeneous spaces. So non-Kähler space, this is a complex manifold with transitive action of a compact Lie group. And then M admits transitive action of compact semi-simple. And then for such spaces, every space which has compact transitive action of semi-simple, compact semi-simple Lie group, which admits actually SKT metric, up to a finite cover again, is a product of this type of compact Lie group or Samuelson space, and something which is called generalized flag manifold. This is pretty much the only homogeneous spaces which admit Kähler metrics. And homogeneous means with transitive action of semi-simple Lie groups. I mean, tori are also, but we don't look. And this proof actually comes from a basic abstraction which Gil Cavalcanti found. This is if we have the 3-0 Dolbeault vanishing and 2-1 non-vanishing, then I mean we may have SKT metric, and this condition is satisfied only if we have this type topologically, this type of spaces, with the crucial gradient here being the fact that the cohomology ring, Dolbeault cohomology of the flag manifolds and generalized flag manifolds, has very specific properties, which lead to the fact that, yes, we need to have actually up to a cover finite compact Lie group. Now, one can use as a remark the fact that for this type of compact Lie groups, any invariant left invariant structure is actually determined by a maximal tori. This is Samuelson's construction, and actually every left invariant has maximal tori, such that in a certain way the structure is left invariant and also right invariant under the action of this maximal tori. It's not against, I mean, the maximal tori in these compact Lie groups all are conjugated, and actually at every point one can find of the group, one can find a maximal tori passing through it. They are kind of dense in a sense. But okay, so I'm back. But using this fact that every left invariant is also right invariant under some action, we showed with Anna that if we go back to compact semi-simple Lie group, then the left invariant SKT metric compatible must be compatible with the bi-invariant metric. And then, as a result, if we have a metric which is both SKT and CYT, which is left invariant, but also right invariant under some the fixed action, then the space is necessary Bismuth flat, because the corresponding metric is bi-invariant, and by the previous result on a compact on a semi-simple Lie group. Now,
Sorry, Gail, can I just interrupt?
later, do you hear me?
Yeah. I wonder, could
Jeffrey?
you go back to the previous slide?
Okay, but you'll need to wait a sec because
Okay,
it
yeah,
uploads slowly. Because yes, a sec.
What what is this argument of? Oh, sorry.
Barbaro, yes. This is using the pluriclosed law as the fact that this metric will necessarily be stationary. And for stationary, he uses a calculation of the Epley group. It's one-dimensional. And stationary with one-dimensional Epley group needs to be necessary eventually by invariant. I don't remember exactly everything.
Oh,
The
okay.
main point is this calculation of the LP11 LP group, which is, I mean, to prove that it's exactly one dimensional is critical in a
I see.
sense. Okay. I don't remember. It was relatively simple use of the closed flow. I mean, the essence is actually the cohomology calculation there.
Okay.
I don't know. Maybe if somebody is in the audience remembers, they can explain.
I guess, yeah, it should just be sort of getting the uniqueness somehow of the
Yes,
uh,
exactly.
of the metric. Yeah,
Correct.
thank you.
It uses the uniqueness. It's kind of using simple argument, from the flow. The essence is, yeah, calculation. As far as I checked, it's correct. It should be. Now, looking at the spaces with parallel torsion, not just closed, but parallel. What we observed, honestly, Beatrice and Anna observed, I only checked in a sense and tried to simplify it whenever possible, was that for a compact space, which is SKT plus CYT, the and assuming the parallel torsion, then the Riemannian holomorphic universal cover, meaning take the universal cover, the corresponding pullback of the complex structure and the metric, is necessarily holomorphically isometric to a product of Keller-Ricci flat and Bismuth flat. And Bismuth flat is necessarily open, or maybe the whole complex submanifold of a Samuelson space. And J2 is, in fact, induced by J, and G2 is the same. In particular, this type of, let's say, trivial examples of SKT plus CYT structures, which are only products of the basic ones, in fact, are not exactly the only ones, but locally are the only ones if one puts the additional condition for parallel torsion. Now, I think Stefan Ivanov, in some paper August last year, showed that if the real dimension is 6, then if the torsion has, let's say, constant norm, it's necessary covariantly constant. It's parallel. So in dimension 6 at least, this could be slightly relaxed and still leads to the same type of rigidity. Now, the proof here is what happens if it is non-Keller, and it's in fact relatively like not hard in a sense, simple steps following the basic result, which is by Zhao and Zheng for the bismuth flat, for the parallel bismuth torsion enclosed without any Keller-Deran factor in the space. And here the idea is if we have parallel torsion, then there is a natural splitting here of the tangent bundle. And of course, in both sub-bundles here, they are parallel. And the first one is, by definition, the kernel of the torsion. I mean, the set X for which TB of X, Y, Z is always 0 for any Y and Z, where we consider torsion as a map from a tangent space to lambda 2, for example. And then F2 doesn't have this sub-distribution corresponding to Keller-Deran factor. This is where this result by Zhao and Zheng go. And then one can see the lift of the structures, how, in fact, because the bundles are parallel, then they naturally determine for simply connected case a direct product. Now, the point is locally, or let's say up to universal cover, these spaces look like this, so we cannot say much. But going back to this construction, which comes from the suspensions, what one can do, what we have done is, again, mostly Beatrice and Anna, is that if we start with a Keller manifold and do this type of suspension, where K, in this case, is a Keller space, S3 is the standard tree sphere, and then this is odd dimensional space. This basic suspension is already even dimensional. This is, if you remember, this MF here corresponds to this product K times S3 times R factored by Z. And Z is generated by this element when psi is this time. The crucial point is that this is actually isometry. And on S3, you take the identity. Now, if this is isometry, then the examples become a lot more kind of different. From the beginning, we started with the so-called hyperbolic suspensions, where this psi was non-isometry, but preserving some homomorphic symplectic form. The result was the space is balanced. Here, what happens is if this G is Ricci flat, not necessarily flat, so K is like Keller-Einstein, then the suspension is, in fact, precisely, well, CYT and SKT or BHE without flat Bismuth connection. But it still satisfies this property that the torsion is necessarily parallel. Well, one of the reasons is this is still like locally a direct product of a Keller space and S3 times R, where S3 times R has this structure coming from as a pullback from a Hopf surface. This is the cover of the Hopf surface. And of course, it does have this standard SKT and CYT structure, this three-dimensional group. And here is a little bit in details the construction. We look at this product, and C2 without the zero is exactly S3 times R, formally R plus, but still the same thing by exponential. And then looking at this type of map for the action, where this time on the second component, the C2 vector X, we act by, let's say, 2 or to power n. And the quotient has this form, which you see here, which is pretty much the direct sum of the Keller metric on K and the Hopf metric on C2 without the origin. The Hopf metric means it descends to the Hopf surface if you factor out C2 by Z. Now, our Z action is actually flipped. We act on both components, but because psi is isometry, and the action on the C2 part preserves the corresponding metric, the result is that the metric descends to DDC closed on the suspension. Now, as a topological structure, this is homomorphic fiber bundle over a Hopf surface. Here, J minus is just a complex structure on the Hopf surface. And in particular, this does not admit a balance metric. Actually, the question here, why this does not admit a balance metric, is again solved by this paper by Michelson. Again, well, we know what this looks like. And the fact that this is diffeomorphic to a product of suspension and the trace layer means that topologically this space is formal again. But this time, the fact that it's non-Keller doesn't require really complicated or delicate arguments. Just the calculation of B1 gives you odd. I should mention that the previous suspensions actually, all of the Betti numbers were even. So this type of argument doesn't provide non-Kellerness in the beginning. And again, you take the Keller surface. Well, let's say K3 surface as an example for this non-trivial. The result will be we have manifold, as you see here, with second Betti number less than 22, which is before that. And this is, in a sense, non-trivial examples. The first, let's say, the easiest non-trivial example of compact manifold, which is CYT and SKT. At one, I mean, that means metric, which is both CYT, SKT, non-Keller, non-flat. And here, non-trivial means it's not a direct product or a finite quotient of a direct product of Keller-Ricci flat and Bismuth flat spaces. But it's still locally one of that. And in particular, okay, one sec, because I see here. Okay, now it looks like the connection is fine again. And this space also have a parallel torsion. So how and whether one can construct the compact BHE space for which the torsion is not parallel is still a question. Now, as a last property for this type of examples, one can look at the same space, and it appears, and it's kind of straightforward, that one can find another compatible complex structure here for which one has a genuine bi-Hermitian structure where the two torsions of the two structures have opposite sign and are closed. So in particular, this mapping torus for this, again, type of generating diffeomorphism admits a twisted generalized Keller structure, which means that the tree form is closed but not trivial cohomology class. And split means they commute. And in these terms, one can see that the bi-Hermitian structure has the two complex structures using opposite orientation. And well, I think this is pretty much what I can say so far. If you wait a second, you'll see the last slide.
Thank you. That was very interesting.
I thank you for the invitation. Maybe as kind of outcome, as in the physics, usually they have this kind of summary at the end, not in the beginning. In a sense, at the current state, the study for this type of structures and metrics is a little bit like initial data collection and observations, and it still doesn't look that nice unified theory, which it should be at some point if this is really nice mathematics. But hopefully, with more and more people interested, I hope this thing will advance quickly. Thank you.
That's the goal. Yeah, thanks.
Hopefully,
are there more
we can find
questions?
something better. Yeah.
Yeah. I was curious. I wonder if you could repeat this thing you said about like in 6 dimensions, there's a weaker condition that implies parallel torsion. Well, you said it was like a result of Ivanov,
Oh, this
maybe?
is a paper by Stefan Ivanov and I think one of the younger people in Sofia. And I think they use the fact that if you have, I mean, these are local calculations and then integration of some quantities which become zero. The result is pretty much if you have SKT and CYT compact space, 6-dimensional, and you assume that the torsion is, let's say, with constant norm, or maybe it has
Oh,
constant trace if you take the Hermitian trace, then the torsion is necessarily parallel.
okay. I see.
And this is pretty much calculation of the norm and integral norms of the torsion and the covariant derivative of the torsion and compare to all of that other terms. I mean, this is like the composition of the tensor into components under UN. And I'm not sure what else is in the proof, but somehow
Okay.
dimension 6 is, I don't see how it can be extended. Stefan has a paper on dimension 7 for analogous question in G2 and dimension 8 for spin 7, I believe, something similar.
Mhm.
And yeah, but yes, this is the one of the recent results mentioned. Of course, if necessary, I can try and find out the paper
I'm sure I could find
here.
it. But-
Yes. And yeah, share, but this is again last, uh, I think last year.
But yeah, it's fine. I can look it up. I'm sure I can
Hey,
find it.
can I ask something?
Yeah, please.
So
Yeah, yes.
is there any good candidate for full autonomy bismuth
Yes.
hermitanism? Do you what do you think is a good candidate for that? Like full autonomy, like autonomy SUN
For full.
in dimension. Yeah. Is
Oh,
that even possible?
actually, if let's say the one candidate I would consider is this 6-dimensional, but they have torus symmetry. And I'm not sure the torus symmetry will not lead to some restriction of SUN to like SUN -1 or something. Like from SU3, you may have to go to SU2, but full, I have to see. It's not certain, but still. And
But sorry, what
yes.
example is that you have in mind that might give SU2 or something?
These are examples which we had long ago of Calabi-Yau with torsion spaces on 6-dimensional manifolds, which are coming from, again, this type of generalized Calabi-Ekman spaces, similar to this Porkushkin ansatz. And that's which Fu and Yao used for the Strominger system. This type of bundle construction with different bases, not K3 surface, one can find CYT metrics on the total space.
But then the question is if they're pluriclosed or not. Is that the point?
They have either SKT or CYT. And the CYT, you have the holonomy SU. But whether inside SU, but whether it is the complete SU, let me try to find to go back to see if get to this place. Okay. When it comes to that, one sec. I will show you in this paper which we had with my brother and Poon. This type of spaces are possible candidates, but I don't promise. You see, this type of spaces here. This means connected sum of that many copies of S2 times S4 and that many of S3 times S3. It's pretty much equivalent to, say, 6 manifold spin with zero Euler characteristic, roughly speaking.
These
And
are
they
known
are
to be
possible candidates.
these
Yeah.
are known to be CYT or pretty close
They are
or both?
CYT.
CYT.
They are CYT non-Bismuth flat.
Okay.
Some of them may have SKT, but different SKT, not the CYT.
Yeah. Yeah.
Okay. But they are natural candidates for like to check the full holonomy. Of course, to check the full holonomy calculation-wise is not necessarily easy because usually the metrics on the base, this is toric bundle over complex surface, and the metrics on the base are not explicit. And these are like blow-ups of CP2 in many points. And then to find explicit metric is not clear. So to calculate the torsion and the holonomy might be, I don't know. It's possible, but I'm not sure that this is kind of clearly possible to calculate. It's not impossible, but still.
Well, I guess maybe one can try to reproduce the
Yeah,
Calabi-Yau case where we know about it. So I don't.
this is possible too. But yeah, this is also not bad idea. Happens. If you want, I can show you the paper by Stefan. I'll stop sharing the screen here.
Sure.
And I share this paper. Okay, you have to wait again. It's loading and slowly loading.